So we've talked quite a bit about the electric potential now and thought about what it is near a point charge and how to calculate it and where to put the infinity. Now let's do the potential near continuous charges. So just like with the electric field, we think about a smoothly charged object. We treat it as a continuum with some charge density. So we thought about the electric field for that. Let's think about the potential. So let's start with the same one. Let's start with my charged rod with some charge density lambda. Right? And it was length L. And before, we said it would be good to set up the coordinate system where we have the rod on the x-axis, like that. And we'll put the center of the rod at the origin here. Some charge density lambda, and we want to know what is the potential at some point up from the center. We can call that the y-axis and put the point right there, point P. And it's at some height above the center A. Right? So how do we get the potential? Just like with the electric field, we don't have a formula for a rod. We have a formula for a point. So we do the same thing. We break the rod up and we think about some little piece of the rod like this, and we call that little piece to have a charge dq. And if you want to know what dq is in terms of x, we know that it's lambda times that little piece dx. So we're going to write the differential potential. What little amount of potential does this create here? And now we can treat this as a point charge, and it's at some radius away. So it's at this distance like that. So we say, okay, then the little piece of potential it's creating, we'll call it a differential potential, dV. And then we think back, well, what's our formula for the point charge? It was K E, Coulomb's constant. The charge is dQ over R. So no integral to worry about. We've already done all that. This is basically just the potential of a point charge, KQ over R. All right. Well, now we just have to add that up for all along the rod, right, to get the V. Right? The potential is the integral. Add up all the dVs, which means we need to integrate this thing. So we have KE here. We need to actually integrate along an axis, so we'll switch dQ. To lambda dx, like that, because we know we're going to add up every little piece going along the charged rod. We're going to integrate the whole rod, so we're going to go from minus L over 2 to L over 2. And we know that everything in the integral has to be as a function of x, anything that changes. Well, this distance that we would usually call r, actually we need to figure out what it is. Well, we have a right triangle here. It's the square root of x squared plus a squared. A is the height, x is where you are. And we're just lucky that it doesn't matter when x is negative because it's squared, so it works for both the positive and negative side of x. So down here we have the square root of x squared plus a squared. So that's it. We just have to do that integral. And this is one that we can't just do by hand. It's one that you got to do some complicated method, or you just look it up in a table. Right? Can't do it by hand. You could say, well, it's x squared plus a squared to the minus 1/2, and you divide, raise it to 1/2 and divide, but that won't work because you got the derivative of this is 2x. And when you try to divide by that, there's no x to cancel it out. So we can't do it. So we will look it up, and in the table, so we'll say, let's see, so V, let's take all the constants out that we can, KE lambda, and we're left with the integral of dx over the square root of x squared plus a squared. So I look it up, and it's sort of a complicated one. It's actually the natural logarithm n, ln. I'm sure you've heard of the natural logarithm, and now I've got to confess something. That the worst thing about teaching a class, especially to this number of people, is you're always very insecure about how you say things, right? So you have some word or a name that you say a certain way, and it's because your teacher taught you that way. And you hope all your teachers said it the right way, because it would be very embarrassing, right, to say it the wrong way. So one for me is the natural logarithm. I was raised to call it lawn, like mow your lawn, right? Log was base 10, but the natural one is lawn. So I'm just going to call it lawn. I was going to try to convince myself to say natural logarithm every time, so I wouldn't potentially be embarrassed. But I'm just going to do it my way. I'm going to say lawn. I hope someone else in the world says lawn other than Mr. Reed, my 7th grade geometry teacher. Okay, so it's Ke, Coulomb's constant, times charge density, linear charge density lambda, times the ln of x plus square root of x squared plus a squared from the table. If you don't believe me, take the derivative of that and see if you get back to there. I strongly encourage you to do stuff like that. Minus L over 2, evaluated from minus L over 2 to L over 2. And now it just really comes down to plugging in. We will get that the potential V is Ke lambda, and it's the ln of this with L over 2 minus the ln of this with minus L over 2. And you know that when you have sort of the, anytime you have a log of A minus a log of B, it's the log of the ratio. Right? So that's also true for natural logarithms. So we can start writing it as the ratio right away. We plug in this, it's L over 2 plus the square root of L squared over 4 plus A squared, and minus, so it goes in the denominator, minus L over 2 plus the square root, and the minus also squares to L squared over 4 plus A squared, like that. You could go from there. You could simplify some more. You can multiply the top and the bottom by 2 if you want to. Let's just do that, and then we'll call it quits. Ke lambda ln top and bottom by 2, that becomes L plus, take the 2 in there, and it cancels that 4. That's convenient. L squared plus 4 A squared over minus L plus the square root of L squared plus 4 A squared. You could try to simplify it more, but you're not really going to do much. Okay? It's always going to look ugly. But that is the potential here. So in principle, it was very simple. It was very similar to doing it for the electric field. But in practice, it was a lot easier, because remember, the potential is a scalar field. We didn't have to think about vectors. We didn't have to do an I component, I hat component, and a j hat component, and think about the cosine and all that stuff. It's just a potential. One term, and we're done. Okay? We have a question here. Let me see. I'm going to break the board. Let's see. Andrea, plan B again. Does it need to be symmetric like that? Oh, yes. Let's see. So what we're asking here. Yes, so I did this in the center, right at this point, right up the center of the rod. And we were thinking about the electric field. We put it there on purpose to make all the x components cancel, so it would just stick straight up. And that let us only do one term. So that was one reason we needed symmetry. Sometimes symmetry makes a problem easier. Sometimes symmetry is required to even do a problem. In these Gauss's law problems, to be able to do the vector calculus without a great deal of difficulty, we like symmetric situations. Here you don't need symmetry. I just happened to put it there. We did nothing here that requires symmetry. You could just as easily have put it here at the end of the rod. We could calculate it there with these similar formulas. We could calculate it here, or anywhere. All it would really do, and the way we set this up, is affect your limits. You could calculate it right here, call this the origin, and then you would integrate from 0 to L. And most of the problem would all be the same, except for evaluating, applying limits to the integral. Or you could do it at this point and call this the origin, and it will also affect the limits of your integral. So yeah, symmetry is not critical in this exact case. Let's do another potential near a charge distribution. Let's do potential near a charged disk. We're going to do it one just to see another one, but also the exam's coming. We want a lot of practice setting up integrals, solving integrals. Be sure we know how to do this. So Let's do one more. So the charged disk would look something like this. Great big disk. I have it sort of in the plane of the board. It's got a radius, we'll say A. It's got a charge density, sigma. And we want to know the potential on its axis at some point out here, a distance B along its axis. All right. So let's see, how do we do it? Well, since we don't have a formula for the potential of a disk, we don't have the formula for the potential of a point charge, we break it up into a little piece of charge. So we say, remember, for the disk, you draw sort of two radii coming out like that, and you say, what I do is I go out to this radius, and I go out another radius. So I have a little thing this way. It kind of looks like that. A little piece of the disk, right? So it's got dr this way. But then to make it, I also had to move around theta. We're doing this in polar coordinates. So you come around here to theta, and then you go to theta plus d theta. So this little distance here is r d theta. So our differential charge dq is just the charge density times this area, and this area is r dr d theta. That's how we usually say it. It's dr times r d theta. So we're going to take each of these little differential surfaces, little dAs, turn them into dqs, and just do our integral. So let's think about the differential potential dV. Differential potential from this little thing, treating it as a point charge, out to here is Coulomb's constant, dq, and here we talked about it, dq is sigma, the charge density, times the element of the area, which is this times that, but we usually write it r dr d theta, sigma times r dr d theta over r. Now, we're mixing coordinate systems. We have two different names for r, so let's not get mixed up. Whenever we use this simple formula, kq over r, for a point charge or a differential element, we're saying we're treating it like a point charge, and we're thinking of spherically symmetric coordinate systems centered on that thing. Right? That's what this r means. That's what this r we're about to put down here means. But we're also doing this problem in a coordinate system of a disk that has its own r sticking out. So sometimes in physics we run out of letters. Okay? We're going to kind of use r twice. That's why I'm actually being careful not to write an r down here, meaning how far you are away from this charge. I'm going straight to the formula that we need, because I'm trying not to have multiple r's for different coordinate systems. That would be bad. Sometimes you do it, you might write an r prime. Ugh, I'm not even going to write that. Okay? So, but remember, whenever you deal with this little thing as a point charge, you're actually creating another coordinate system. Usually you create it, you use it, and you get rid of it. That's what we're going to do now. There's a spherical coordinate system here. We've got to get to r, but we're not going to call it r. We're going to call it this distance. And what is this distance? Unfortunate place to write a b. There, it's a right triangle like that. So it's b, and what is this? This is r in the polar coordinate system. This is r of the disk. Okay? So this is the square root of r squared plus b squared. Again, we're only ever writing the r of the disk, of the thing we're actually integrating. The square root of r squared plus b squared. And you also have to be careful that r's and sigmas look quite similar. So let me redraw a couple of r's and a nice curvy sigma. There you go. So sigma, r dr d theta, is the dq, and in the bottom, this distance is this, from Pythagorean theorem, the square root of this little r squared plus b squared. There you go. That is pretty much everything. So now, let's do the integral. It's a two-dimensional integral. We need two integrals on there because we have to integrate over dr and d theta. So two sums. Let's see. So let's put the theta on the outside. And the theta, we're going to integrate, start here. We're going to go all the way around the disk to be sure we capture all the little dq's. So that's going to be 0 to 2 pi. And the r, to capture all the little areas, we have to go all the way from r equals 0 to r equals a. 0 to a. Okay. Now the ke doesn't matter much. Now let's go and keep it in here. Ke And the sigma, it's not going to do anything. Put the sigma right there. And then let's put all the r parts together. R dr times the square root of r squared plus b squared. And then the only theta part is just d theta. Okay. So we'll integrate this outside part first. If we integrate d theta, we just get theta. And if we evaluate it from 0 to 2 pi, we just get 2 pi. Depending on what books and notes you're reading, people might not even show that integral. They might just say, oh, there's 2 pi. Right? If nothing changes with theta and you got to go around, it just adds a 2 pi to the equation. So we could actually do that. Here, we'll just do that live. We'll say, oh, actually, this could go away. And you could just write 2 pi. I showed you the integral because, you know, I'm watching your back. Okay. So let's see. So now let's do the r integral. This one we can do by hand. Let's see. V is, let's keep our constants out here, 2 pi ke sigma. And it's really the integral of r times r squared plus b squared to the minus 1/2. Okay. So you raise it to the plus 1/2 and you divide by that 1/2, which means you multiply by 2 r squared plus b squared to the 1/2, and then you also divide by the derivative of that, which is 2r. When you divide by the r, it cancels that r. You divide by the 2, means you multiply by 1/2. Hey, those go away. Look at that. And you evaluate it from 0 to a. Okay. Let's see. And now, all we got to do is apply our limits. So the potential V is 2 pi ke sigma. And let's see, it's a square root of a squared plus b squared minus two terms, the square root of a squared plus b squared. And we plug in the a minus all this stuff again, and the square root of, that's 0 b squared, so it's just minus b. Square root of b squared is b. Okay. So there's your potential off the axis of the disk. And like the electric field, this is another case where actually we've now solved it for any position on the axis. Okay. So we have a b here, and the b is right here. But if you wanted to say what's the potential as a function of distance, you could call that the z-axis, and the b just becomes z. You know, you could make a plot now of the potential as you move away from the axis. And just like the rod, in the rod problem, like Andrea Plan B asked, what if you move the point around? Here you could change this problem a little bit without having to do a lot more work. You could do a washer. What if it looked like this? What if it had a hole in it? Okay. What if the charge were just out here with some charge density sigma? All that would change is this. Okay. Instead of integrating from 0 all the way out to catch the charge, you just have to integrate from, say, R1 out to R2. So if that's R1 and that's R2, you would just change this, integrate from R1 to R2. It would change the limits. It would still give you the answer. So a lot of times you set up the integral once, it can actually solve different kinds of problems. One more. This one is called, there's more than one way to skin a cat. Perhaps you've heard that phrase. I didn't just, make that up. The early electrostatics people definitely knew that there's more than one way to skin a cat. So let's solve one more problem of a potential from a continuous charge distribution. Let's have a spherical charge distribution. Right? So a uniform sphere of charge q, okay, and radius a. Okay, so we can say right here from the origin out to some radius a, and it's a sphere, like that, full of charge q. So if we're going to do this, and the question is, yes, what is the potential at the center? Of the sphere. There's charge everywhere. One way you could do it is what we've been doing, is an integral, but this would be not a fun integral to do, because you'd have this point, and you have to think about little volumes of charge out here. Inside the sphere, if you move out, difference in radius, kind of like that, and then you'd move an angle like that, but you'd move in another angle, sort of spherical coordinates have 3 angles to them, or 2 angles to them. You have to make a little differential volume element. You have to write it in spherical coordinates and do the integral in 3 dimensions. It's doable. There's nothing wrong with doing it that way. You can do it. And add those up and get the potential. You could definitely do that. But I want to show you another way you can get the potential, and that's from Gauss's law. Remember, Gauss's law gives us the E field, and from the E field we can get the potential. So this is sort of a sidestep if you don't want to set up the integral. And if you have something that's highly symmetric and you've already solved the problem, say, with Gauss's law, then there's no need sometimes to have to work so hard. So let's remember what Gauss's law told us about the sphere. It told us that if we were to plot the electric field versus radius, say the magnitude of the electric field, symmetry tells us it's always going to point out or it's always going to point in. So the direction is always radial. But the magnitude, recall when we did Gauss's law, is that it went up sort of linear like that at first. And then when you got to the edge, then it acted like a point charge at the center, and it came down like that. So we have a plot like that in the Gauss's law section. In here, the actual form of it was KQR over A cubed. I think it has to be cubed, right? Yeah. And this is the linear part. It's linear with R. And then on the other side, when it's coming down, then it's just like a point charge, KE, these are Coulomb's constants, KEQ over R squared, standard point charge formula. So we already have the E field. We want the total potential here. Well, we want the potential difference. Let's go back to thinking about it as a difference. So when we have our point charges, we can always assume its potential is 0 at infinity. But let's get the potential at the center by first assuming the potential equals 0 at R equals infinity. We always assume that. It's just when it gets a little more complicated than a point charge, you want to remind yourself and you want to write everything out in a little more detail. So what we want to do is get the delta V going from infinity to R, or to the point we care about, right, the center. Because we're trying to find the potential of the center. And if it's a difference, it's the final minus the initial. Okay? So if we write this delta V from infinity to 0 is what we're going to do. We're going to change the radius position from infinity, bring it to 0. Because that's going to be equal to what? It's going to be equal to the potential at 0 minus the potential at infinity. Okay? Because the difference is always final minus initial. And we've already said that this is 0. This is 0 at R equals infinity, so that'll go away. So solving this actually does give us the potential at the origin for the case that it's 0 at infinity. So we just have to write that integral. Well, delta V is minus the integral from infinity to 0 of E dot ds. All right. Well, now we have to plug in for E. We have 2 domains. Which one do you use? The good news is it's an integral, right? An integral is a sum, so you just break it up into 2 sections. So this is equal to minus the integral from infinity to A, right? We're going all the way from infinity to come up to the surface, A, that's here A, infinity to A, and there the E field is, out there, it's KQ over R squared. KEQ over R squared. And remember, it's this R hat dot ds. And then we need to do the rest of the problem, minus another integral, keep summing from A to 0. Okay, like that. So now first we went infinity to here, and now we're going from here all the way to there, where we were trying to get. And that's E dot ds. E is KEQR over A cubed. KEQR over A cubed, and also R hat dot ds. Okay. Well, one thing that'll speed us up and save me a little board is that r hat.ds, remember that's just dr. Everything's spherically symmetric, so we can just write those as dr. R hat.ds just picks off the changes in radius, because in this case, changes around the circle don't matter. So we've talked about that before. And now we just have to do the integrals. This we saw before, that's to the r to the minus 2, becomes r to the minus 1. You divide by the minus, it cancels that minus, and you get KEQ over r, same as when we did a point charge, from infinity to a. This one is r, so it becomes, the minus stays, it becomes minus 1/2 r squared when you just integrate r. So minus KEQ r squared, and then the 1/2 makes it a 2a cubed. Evaluated from a to 0, like that. All right. And now I've run out of board, so I'm going to pull this up. And we only need about one more line. So let me see. If we keep going, then we're going to get delta V is, we decided it's V at the origin minus V at infinity, which that's nothing, so it's really just the potential at the origin. So here, this is KEQ over R. KEQ over, we plug in the A, so over A, minus KEQ over infinity, but that's of course 0. So there is the potential of the point charge if we go just to the point A. But then we have to go further. We have to keep adding to the potential. This becomes minus, and let's say we plug in 0, and what do we get? Oh, we get 0. Right, so if you plug 0 in for r squared, you get 0. And then minus, and we've already put this minus out here, so that's minus gives us an a there. So that's KEQ a squared over a cubed. Boy, what a mess. Let's see. So in the end, all these, so many zeros, right? That's 0. In the end, we end up with basically the potential at the origin. We have KEQ over a here. And actually, we have minus, minus is plus, and those cancel. We have KEQ over a there. They both gave the same thing, and they're both plus, so they add. So we get 2 KEQ over a. Something's fishy here, and there it is. I know you saw it, and you were all excited, and yeah, okay, I know. 2, I missed this 2. I knew a 3 had to work its way in here somewhere. I knew there was a 3 in the answer, and a 3 does show up now because we have KEQ over a, and basically a half of that, KEQ over 2a. So when we combine them, this is 2 over 2, right? So 2 plus 2 is 3, so it's 3 KEQ over 2a. And then that is the total potential at the center of the sphere.